Hey everyone, welcome back in physics class. In previous video lecture, we started chapter 11, which is dual nature of radiation and matter. I told you about experimental arrangement for the study of photoelectric effect. As you can see in the diagram, I have told you also that electrons will be emitted when any light will fall on this cathode plate C, which is also called as emitter plate. So when electrons will be ejected, these electrons, they have a particular name as they are ejected because of photons. So these electrons will be called as photoelectrons. So as you can see, they are moving from cathode plate C to anode plate A. So as electrons are moving, and we know that moving of electrons means there will be a current in the circuit. There will be current in the circuit, and that current will be called as photocurrent. These electrons will be called as photoelectrons, and the current constituted by these electrons will be called as photocurrent. So in today's video lecture, we'll have a look at how we can use this experimental arrangement to study various parameters with relation to photocurrent. And the parameters that we are going to take up, the first parameter is intensity, second is frequency, third is potential difference between the plate A and C, and fourth is the nature of the material. So very first parameter that we are going to take up today is effect of intensity of light on photocurrent. Photocurrent, you have understood, that is basically what when electrons are moving, they constitute a current. And just because this effect is photoelectric effect, so that electrons, they have a particular name, photoelectrons, and the current constituted by them will be called as photocurrent. Okay, so we are clear with this word. Now, what is intensity? What is intensity? Intensity means number of particles per unit area per unit time. So here we are talking about intensity of light. So intensity of light will be what? It will be number of photons per unit area per unit time which are falling on this cathode plate. Okay, which are falling on this cathode plate. So obviously number of photons striking this cathode plate, if you are going to increase the number of photons which are incidenting on this cathode plate C, then what will happen? More and more number of electrons will be ejected out. And both are directly proportional to each other. As you can see the graph which is drawn over here in figure number 11.2. So if I am going to plot intensity with photoelectric current, what will happen? They both are directly proportional to each other. Okay. So as always, I have told you that whenever we have to plot a graph, there are two parameters, and how to decide which we have to take along x-axis and which to be taken along y-axis. So independent parameter we have to take along x-axis. So in between of photoelectric current and intensity, which one is independent? Intensity is independent, that is in our hand. I will decide that how many photons will incident on plate C, and photocurrent depends on it, because more intensity means more photocurrent. So this implies that number of photoelectrons emitted per second is directly proportional to intensity of the incident radiation. Okay, second parameter that I am going to take up is effect of potential on photoelectric current. So see, as we are discussing that here are four parameters: intensity, frequency, potential difference, and nature. So what we have to do when we are keeping one as variable, let us suppose if I talk about the first effect of intensity of light on photocurrent, here I want to see the effect of intensity with respect to photocurrent. So other parameters I am keeping constant. Okay, you cannot see the effect of all the parameters simultaneously. So as in second point, I want to see effect of potential on photoelectric current. So potential will be the variable, and other parameters, they will behave as a constant, right? As I've highlighted also that light of fixed frequency and fixed intensity. So frequency and intensity, we are keeping it constant. Okay, so the graph drawn here is 11.3. What I have to do, see, there are two parts of the graph. There is left hand side also and right hand side also. So I'm going to make you understand turn by turn. So first of all, I'm just going to tell you about the right side of the graph. Okay, let us see for the intensity I1. So what is happening? See, as I have to move towards right hand side, So I'm increasing what? Collector plate potential. Collector plate potential is increasing, means collector plate was anode plate connected to positive terminal of the battery. Means if you are increasing collector plate potential, means what? You are making anode more positive. You are making anode more positive. So more positive is the anode. What will happen? More attraction, more number of electrons will be attracted. If more number of electrons will be attracted, what will happen to photocurrent? Current is what? Nothing. It's just the what? It is just the motion of electrons. So if number of electrons, they will be attracted more, photocurrent will increase. Okay, and as you are seeing linearly, like a straight line parallel to collector plate potential, that is basically saturation current. Means maximum number of electrons which were free, they have been ejected out of the cathode plate. Okay, so a point will come where all of the electrons, free electrons, they have been ejected. So a saturation point will come. So if you see for I2, that is for different intensity, and I2 is greater than I1. Now what will happen? Greater the intensity means more number of photons are striking on cathode plate, more electrons will be ejected. So obviously photocurrent will be more. And for I2, if you are going to increase the collector plate potential, photocurrent will again increase. So saturation value of photocurrent for intensity I2 will be greater as compared to I1. And again, if I am going to contain one intensity I3 which is greater than I2 and I1, what will happen? Saturation value of current I3 will be more as compared to I2 and I1. Clear? Now let us have a look on the left hand side of the graph. As you can see here, the potential is decreasing on this side because we are moving towards left hand side, so potential is decreasing. What do we mean by the decrease in potential? By decrease in potential means that we are making anode less positive. By decreasing of potential means that we are making anode less positive. So by making it less positive means less attraction, lesser number of electrons will be attracted, lesser will be the photocurrent. So as you can see, photocurrent is decreasing. And a point will come means you have reduced the potential of anode plate to such an extent that no electron will be attracted by the anode plate. And at that point photocurrent will become zero, because no motion of electron means no photocurrent. So the point at which, or the potential at which, the value of potential at which photocurrent stops or becomes zero is called cutoff or stopping potential. And it is denoted by V0. Why negative sign is there? Because it is lying in the left hand side, so obviously it will be having negative sign. There is one more definition. In other words, we can say photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectron. Even the most energetic photoelectron is not attracted by the potential, or it is stopped. So we can say that, or we can write K maximum as EV0. How they have written? K is what? Energy, kinetic energy they have written. E is what? Charge, and V0 is the stopping potential. So as we have written, we have done it also. Potential energy, U is equal to Q into V. So from here we have taken another form of energy, that is what? K maximum, which is EV0. Okay, and this formula is important, we are going to use it later on. So from this graph, or from this point, we can conclude that for a given frequency of incident radiation, the stopping potential is independent of intensity. As you can see on the right hand side, we were having different amount of saturation current for different intensities, but stopping potential is same. They all are going to stop at a common point, means stopping potential is same. So stopping potential is independent of intensity. Okay, next point is effect of frequency of incident radiation on stopping potential. So before doing this point, I just want to tell you that energy of photon is equal to h into frequency. What is h? It's a constant and its name is Planck's constant. Energy of photon is equal to h into frequency. So now let us have a look at the graph, figure number 11.4. Okay, so the graph is in between photoelectric current and collector plate potential, because I just want to have a view that how frequency varies with stopping potential. Okay, in the figure number 11.3, I have observed the relationship of stopping potential and intensity, that stopping potential is independent of intensity. Okay, but in figure number 11.4, we are going to view that how frequency varies and how frequency is related to retarding potential. Okay, so two examples I have written over here. First example I am considering, dekho, let us suppose energy is how much? 14 eV. For example, energy is how much? 14 eV, and this energy is of whom? It's of photon. And let us suppose the material that you have considered, the metal you have considered, that material or that metal is having work function of 7 eV. Okay, incident photons energy is 14 eV, work function of that metal is 7 eV. So work function was what? Work function was the minimum energy required to eject an electron. Means 7 eV will be used by the metal surface to eject that electron. So electron will be carrying how much energy with it? Are you getting my point? That we are providing how much energy? 14 eV. Okay, but metal is going to use 7 eV. Why? Because that's the value of its work function. So that 7 eV, the metal is going to keep it with itself and will allow the electron to move out. Okay, so how much energy electron will carry with it? Electron will be carrying 7 eV. Now let us suppose frequency you have increased. Now you have increased the frequency. So what will happen? As I've told you that energy of photon is what? H into frequency, some constant into frequency. If you're going to increase the frequency, what will happen? Energy of photon will be increased. Okay, so the energy that you are providing to the metal, that is going to increase. Let us suppose it becomes 16 eV this time. It is now 16 eV this time, but work function will remain same. Why? Because the metal is the same. What I have changed? I have just changed the frequency of the incident radiation, but the metal or the material that I am going to put that light on, that will be same. Work function is 7 eV. Now this time, how much energy will be carried by electron? Will electron carry more or less as compared to the earlier case? It will be carrying more this time. Reason? Because you are giving more. You are giving how much? 16 eV. Metal is going to keep how much with it? It is going to keep 7 eV and will allow the electron to move out. And how much electron is going to keep? Electron will be carrying 9 eV. So if energy of electron is increased with the increase in frequency, if energy of electron has increased with the increase in frequency, then potential required to stop that higher energy electron will be more or less. So two electrons are there, one with 7 eV energy for the particular case, and for the other case we are having 9 eV energy electron. Okay, so let us suppose these two electrons are the electrons with maximum energy, right? So if you have to stop a 7 eV electron, you will require lesser amount of potential as compared to stop the motion of 9 eV electron. So it means I can conclude that if frequency is increasing, the value of stopping potential will also increase. The value of stopping potential will also increase, and the same you are going to observe in figure number 11.4. See, nu3 is greater than nu2 is greater than nu1, means frequency 3 is greater than 2, which is again greater than 1, and simultaneously the value of retarding potential is also following the same pattern. The retarding potential is also following the same pattern. So I can say that with increase in frequency, stopping potential will also, the value of stopping potential will also increase. Okay. Now the figure number 11.5. As we have seen that stopping potential and frequency, they're linearly. How? Because the frequency will be more stopping potential will be more. So graphs will be straight lines. Graphs will be of straight line. But can you tell me what is the reason of this this value, that for some period of time it's 0? For some period of time it's 0 and it is not starting from origin. The reason behind it, as I have told you, that minimum amount of energy is required. Minimum amount of energy needs to be supplied from outside to eject an electron from the metal surface. And energy is what? Constant multiplied by frequency. So if there is a level for minimum energy, then I can say there is a level for minimum frequency as well. Yes, we can say that. And that minimum frequency is called as threshold frequency. That minimum frequency is called as threshold frequency. So this value nu naught, this is basically threshold frequency for metal A. When this supplied nu will be greater than nu naught, then only electrons will be ejected. And similarly for this metal B, as you can see, nu naught dash, that is a threshold frequency for metal B. And when the supplied nu will be greater than nu naught dash, then only metal B will allow its electron to be ejected out. Okay, in today's video lecture I have told you about 4 graphical variations with respect to photocurrent. First parameter was intensity, second was retarding potential, third was frequency, and fourth we have seen the relationship of stopping potential and frequency. And from this graph 11.5 I have defined what is threshold frequency. So go through each and every topic thoroughly, and if you have any doubt then let me know. Okay, till then, take care.